Okay, so hopefully a good weekend. So today we're going to talk about some additional regression topics in Chapter 8 and look at some data sets. These really focus on the different model assumptions that come up in regression, how you might assess them in a data set, and then what you might do about them. And there's kind of a little subtle discussion about how do some of the different assumptions, if they're violated, if it doesn't quite exactly match the model, what does it do? And there's a little discussion about, kind of interesting, if you do transform the data, like square roots or logs, how do you go back and how do you make sense of that statement? So this is kind of, to me, some useful descriptions in there. So our regression model says that the yi's are beta 0 plus beta 1 xi plus errors, and it's in these errors that a lot of the assumptions are encoded, that they're independent of each other, and normally distributed with a constant variance across all the observations, and there's this linear form for there. So the assumptions, basically, that is a linear relationship. You could see this violated if it's nonlinear, of course, but if there are some outliers that really seem to be not part of that population, they might look kind of funny, or the regression line might be pulled towards them, so it could distort where the linear pattern would go. And so that's, to the degree that it might be somewhat linear, it's kind of the degree to which that doesn't work is going to play out to see whether the model's useful. There's constant error variance in the model. Right? And if that's not the truth, if it's not constant, well, our estimates of beta 0 and beta 1 didn't really involve that. So on average, we still get, so if non-constant, we still can estimate the linear regression function, and on average, we're unbiased for that. But the standard errors for different things, the standard errors for the estimations of beta 0, beta 1, or the estimate of sigma squared, well, it doesn't really make all that much sense because it's changing across there. So if it's non-constant, standard errors can be inaccurate. So that if you really had the model underlying it that had unequal variances and could estimate that, you would either get smaller or larger standard errors. And so your confidence intervals could be larger or would be wider, most likely. And so you're making a precise statement, but it's not really warranted. Normality, and then the independents are the other ones. So let's put something about normality. Normal errors. Okay. So you can look at a data set Y, and it can, just a histogram of Y can look very, very non-normal. You can have clumps, it could have multiple modes, it could be skew. That's not really a problem. It's conditional on X's. Are the residuals normal? Right? And so if these are non-normal errors, right, like with any of these deviations from the assumptions, it's a matter of degree. If there are some that are massive outliers and very large errors, and so or if it's very skewed, a bunch of small ones, the degree to which it's non-normal can have more of an impact. But there's kind of a couple things going on, right? There's the estimate of the coefficients. There's less impact on the standard error of coefficients. Beta 0 hat, beta 1 hat. Right? because they're combinations of many random variables. They're the sum, involve the sum of all the yi's together, kind of weighted by their x's and the variance of the x's. So even if the errors are not quite normal, but deviate from that, it has less impact on inference of the coefficients. Just like if the data itself in just a one sample problem weren't normal, but it's not too bad and you're averaging together a lot of observations, then the sampling distribution is still roughly normal and things work out pretty well. But a small sample size and extreme non-normality, things go a little bit, work a little bit less well. But it does have more impact on prediction intervals. With our prediction intervals, well, we don't see using the normal distribution, but it shows up in the t distribution. It's symmetric, and so with the prediction intervals, if the errors are not normal, can be impacted. Maybe the intervals are too small, or they become extremely wide, and it can go there. So it kind of depends on what you want to use it for. Right? This last one, independence. This can be very, very important. If there is a different structure in the data, right, that there's high dependence and they're not really independent of one another, pretending they're independent can cause you to be way over optimistic about things. Right? And that particularly predicting into the future, instead of being normal errors, if they kind of accumulate and all get big or all get small as residuals all in a row, your prediction could be way off. Right? This can be a very important, large impact on standard errors of estimates and of predictions. Large impact on data is possible. And if there's any chance that there's actually a dependence that you could incorporate in the model through time series or geography or something else, then it's probably wise to think about doing that if at all possible. Right? So how do we tell about these different things? Right? Well, some things, like the independence thing, is you're going to need to know something about the data collection process. Right? What units actually are being measured, how were they measured, how were the data collected, is there something that you need to be aware of? So how do you check these things? Assumptions, well, just know about data, data collection, how was it done, the time series, are there subgroups where data are collected in different places, and in general, we would move beyond simple regression with one predictor to try and incorporate some of those things. Scatter plots. In the book, there's a figure 8.6 that we can talk about briefly, but it's by, I think, looking at examples like they talk about there and their explanations of what's going on. What would you see in a figure? Would you see non-linearity? Would you see increasing variances? And some idea of what you might do about it. We'll look at our scatter plots, looking for that. Residual plots is usually a plot of the residuals, the yi minus yi hat, often called EI in other books, over the yi hat. Or you could put xi down here, either one. In the simple linear regression, there's a one-to-one relationship between those because one's just a linear function of that. In multiple regression, you could have multiple x's, so you could put any of the x's down there, or you can put the predicted values there to look for extra patterns. you can look at the residuals versus time. Right, so if there's a time order to the plots, and you suspect that there is some correlation in the errors, you can plot that. You can do the residuals versus the index. So if the data are listed in the data set, one up to n in the data set, and there's some time order or some ordering somehow. The data, maybe it's geography, maybe they're grouped by centers or data collection points. Surveys that are coming in the web usually are time stamped. So if there's something going on, sometimes people find errors in the data collection process, and then they change something. So there will be kind of a shift there, and the error that they correct at one point in the data collection process could have other impacts on other variables, right? And you wouldn't know about it until you look. And then normal probability plots. For some of the types of things that we might look at of the residuals, right? So that would suggest whether they're normal or not, right? The things that are in this little figure, I'll draw some of the things on the next page. You can look at in the book as well. Right? So, figure 8.6 in the book, it's on page 214. Right? We want a relationship where there's a kind of a linear increase and kind of a similar standard deviation or spread all along. And so if you look in little strips along here and little strips along here, they're kind of about the same, size of area of prediction of the points within there. I'll draw a few more just to get a few more points in that kind of show up in those, right? And so as you slide that little window along there, you should basically come up with a straight slide, able to kind of encompass most of the points, and kind of a similar, right, that there wouldn't be a lot sticking out on either side. But sometimes the pattern is disturbed, deviates from that. So this was their A, that would be good to see something like that. A second pattern they show there is, that between X and Y, maybe the points are kind of in here, kind of going up, and then the points kind of change direction a little bit and maybe flatten out. You could have a pattern that looks kind of like constant variance. After a while, mostly linear here, kind of linear here. It's kind of piecewise linear. So what can you do about that? If it's kind of like this, it's kind of hard to do much of a transformation or anything to get rid of that pattern. It's just kind of a fact of life. You could possibly break the range somewhere in here and fit one curve like this and one curve like this. Maybe that if there's a justifiable place to make a break like that, you might do that. There are methods for feeding kind of piecewise nonlinear functions. On the other hand, you might do pretty well to kind of get a quadratic approximation in there. And so in that, when we look at multiple regression, it's going to be fitting a curve that has, so then yi, there's a beta 0 plus beta 1 xi, plus you can put this squared terms in here, the square of a variable. And now this gives you a quadratic equation that can model a curve. And you go up to cubic or higher terms for some things, right? And it might fit. In the part C of their pictures is one that is, if the data really is kind of curving, like kind of going up and going down, if you do ever see something like that, you might, it could also go the other way. That could be kind of going up and a little more curvilinear than straight. And it might just be subtle, right? In just scatter plots then a quadratic might make a lot of sense to fit those. The other pictures they have are a little bit different, that sometimes you will see points that it's kind of together, and then as it gets bigger, these things spread out. So this one would have non-constant variance. You could call this increasing variance. In the variables, and so again, that's you can fit a linear regression like that, you will get unbiased estimates, but they're not necessarily the most efficient. If you could take advantage of the fact that there's low residuals down here and bigger residuals up here, you can do something better. So there's a technique that we can look at a little bit later called weighted linear regression. That essentially allows the weight to depend on the x's, or the square root of the x's. So you capture a little bit of that information. Basically, you put a model into this as to how the variances are changing, and then you change your estimation strategy to deal with that. Alternatively, taking something like the square root of y or the log of y might eliminate a lot of the problem. Right? Taking the square root could make these less spread and won't maybe affect the spread so much because they're smaller numbers. And if you make that other plot, then it might work out. Another one that they talk about, you can have a lot of your points in here. This is number E, not a residual. The x's and y's, and it might look, for the most part, pretty good, but then there might be kind of a number of points that are out like that. So if you fit a regression line to this, these points are going to pull it up. It's not just one point out there necessarily, but the resulting residuals, these distances, are going to be pretty skewed. There's a bunch of really big ones, and then a bunch of small ones, and so the histogram of residuals, like a histogram of residuals, could have a bunch of small ones down here, right, and then some bigger ones. So for some things like that, there's not always that much that you can do about it in terms of transforming the data or changing things. In multiple regression, maybe there's another variable that would predict why some of these are so different up here than the regression line. Maybe there's something extra going on impacting their y outcome values, and maybe if you knew about that, that would explain it a little bit. So you could maybe incorporate another variable. But you might just have to say that the data residuals were kind of skewed. And so take all the predictions and intervals that we give with a little grain of salt, that they're, particularly if there's a smaller sample size, if this is not a really big sample and there's those outliers, it just becomes a limitation to note, right, for things. So but what happens if you're we're going to talk about taking transformations, and on Wednesday, Yefei is going to talk about transformations a bit more. Right? So if the ordinary model is beta 1 plus beta 0 plus beta 1 x naught plus this residual, so that the mean of y given x, the mean function is this. So if you change x by a certain amount, x equals, a new x is you get a little delta x, a little change there. Then the mean of y at this new x prime, minus the mean of y at the original x, is this beta 1 times the amount that x has changed. And that has a direct interpretation of what the slope is. Right? So as x changes by amount, you get beta 1 times that. But what if you do log of y, beta 0 plus beta 1 xi plus epsilon I. So you transform the y's, right? The right. So right. So it suggests that instead of looking at the means, right, the mean of normal distributions, when you take it, you raise it to a power or log it. It's a nonlinear transformation, so the means don't directly go to the means. But the medians, the center of the distributions, do map to one another. Right? The center on the log scale and the center on the regular scale. What was the median on one, it transforms the median of the other one. So the median on the log scale, say beta 0 plus beta 1 xi, in there, I guess I wanted to write that a little bit differently. Right? So we get what I really wanted in there. Try that one more time. So the median value of y at a value of x, right? So we want some x in there. Right? Well, the median on the log y is the beta 0 plus beta 1. So we would raise that to a power. Exponentiated to go back if this log is natural log. Well, what happens if we look at the median of y at, say, x plus 1? Well, the average value of y, not the average, the median value of y for a given x would here be, beta 1 and then xi plus 1. So I dies on there. And so the difference, the ratio of these two, right, the ratio of the medians, gives us something. So if we get the median of y given xi plus 1 over the median value of y at a given value of x, the ratio of these two things is just e to the beta 1. So one unit change in x gets reflected in the parameter. There's a log change, well, the change of one beta 1 on the log scale, but on the original change, if you're thinking about it as the center of the distributions, it gets multiplied by that e to the beta 1, right? So often the coefficients that you're going to get estimated, you'll exponentiate them and think about that in terms of a change. And it's really about the change in the medians rather than the means that it makes the most sense. So people probably think about it similarly. Right? And in that section on the book, there's a couple other examples of how you change things and how to go back and forth. So it's just kind of interesting to pay attention to a little bit, I think. So let's look at some data examples in some of these transformations and see and patterns and see what we see. Okay, let's get some experience with these. So the handout has some code that's there. And the first data set that's used as a case. Okay. Case. Well, it's there, so make sure that's done. Okay, so it's there. Now I'm going to detach this one because it's a little extra thing. Okay, it's there. This is a small data set, so we can actually look at this is the areas of islands, and then the number of species that are there. And so can we use the areas to predict the number of species? And it's pretty clear that this is pretty skewed distributions for area. So if you plot it, this little plot, right, it's kind of sparse, but you clearly, maybe you can judge that there's linear, non-linear. It's kind of hard to judge anything from that small point. If you fit the linear model to it, right, the summary of the output for area as a predictor is the small values of the coefficients, but they're highly significant. It's a very, very small value for the coefficient because we're going from this 40,000 square miles down to hundreds. So it has to convert from these x's to that scale, so you get this little tiny value. Yeah.
Just to clarify, when we call the linear model kind of test, the p-value that it comes up with and the t-value, that's going to be used to, like if we have a p-value less than 0.05, we want to reject the idea that the linear model is a good fit for it.
So if this is this p-value, so the null hypothesis testing is that the area is not a useful predictor. Right.
Yeah, okay.
Right. And so the slope.
According to a linear.
Yeah, the null hypothesis is that the slope is 0.
Okay.
So if we get a small p-value, we're rejecting that and concluding that there is a slope.
Okay.
Right. So in this one, even if it's nonlinear, there's definitely kind of a slope going up. And so this one's going to be significant. One thing you can do with something that's so, the scales are so different. If we did if we divided the area by 10,000, say, right? Oops, by 10,000, you just do a little trick in R to tell it to do that. But if that's done, then we summarize that thing. It changes the coefficients here now. So per 10,000, the plot would be made different too. So area divided by 10,000, say, area by 10,000, and then put the species on here. It's changed from this 40,000 scale down to this, and now the coefficient, for every 10,000 area, you are predicting another 21 species. So it's a little easier to talk about what it means. It's hard to talk about the coefficient we had before. Every foot you increase area or square mile you add, you get 0.002 new species. It's a little harder to think about what that means. But if it's 10,000 square miles and 21 new species. So it's even if you are unsure whether it's linear or not, we can put the line on there. We will talk about the ANOVA table in just a bit, but there's an analysis of variance table that divides the total sum of squares of variability in y into part for the regression and part for the residuals. The sum of squares will be based on the y, but this is the part that's due to the area and mean squares and an f. And again, this tests the null hypothesis, like before, that there's no relationship. Right? So the null is that instead of having a slope line, which should be flat, and should be no trend, linear trend. And it's the same p-value that's in there. So let's save the fitted values, the predicted values, and the residuals into our plot. This is what it looks like in here. Again, there's so few points, it's hard to see too much. But what you might note, if I put in a horizontal line at 0, the average residual is actually 0. But it starts out with some below and then some above and one down below. And that reflects where that line went, right, on fitting these data. Because it was kind of curved, a little nonlinear, it has to find a way to try and fit these things. And because of that nonlinear things, it's somewhere below, then above, and then below. And I know it's a small data set, but it comes through in that. So some things that are a little harder to visualize when it's tilted, particularly at a steep slope, once it's made into residuals, it pops out a little bit more. Right? You can see things a little bit more. Right? If we looked at the species and the areas, particularly the areas are pretty skew. So we can consider doing logs of both variables. It's a small data set. That's log of species, log of variables. They look flatter. They don't look normal particularly, but they are much less skewed. If you take the log of both variables and regress them on there, we can call that the second mon. And the summary of that one, again, is still statistically significant. There is a slope. Let's put the plot on there. And now these, right, after taking the logs of both, looks a lot straighter. Even this small data set looks kind of straight. And if we put the AB line on there for the second model. And it's saved. It's kind of nicely going through the middle of the different points. And if we plot a residual plot, you don't actually have to save those things, but put it in there and then do the horizontal line in there. Some are above, some are below, but it's not kind of divided as much. So it seems to improve the use of that model over there. And this brought to mind other data sets that I've used in different times. There's this applied linear regression book. The different regression book that would be used possibly in 351 class. They have a data set called Cathedral that is the length and height of different cathedrals in Europe. And so there's the length of them and their height. This is not actually the one that I was thinking of, but that one looks like a pretty good relationship. I wouldn't necessarily do much with that one. There, in the second edition of that book, there was a data set that Stephen Jay Gould had on the perimeters and areas of some churches, right? And so this is just entering the data in, and this one, if you plot it, this is what these data look like. Right, so the perimeter is in, I don't remember what the units are exactly, but the perimeter is the area all the way around, and then the area is the square area inside. So in this case, we have something going on where this is in a square feet, and this is in just linear feet or hundreds of feet. So one's a square and the other one's not, and it kind of has this curved relationship, right? It's subtle. You could fit a straight line to that pretty well. So if we fit that model to those data and put the regression line on these, it seems to be pretty reasonable. But right, if you look at it closely, you'll get a few points over here above. These are kind of below the line, and then it kind of comes up again. So that the effect of the curvature, even though it's slight, does make it this kind of pattern to the residuals. Right, so if we get the predictions and the residuals and do this residual plot, right, you end up with this kind of funny pattern in the residuals that pops out, just as much more apparent on the residual scale than it was on the original one because of that steep slope. It's kind of hard to see that curvature. So, thinking about this, right, perimeters in one dimension, right, and the other one's in 2 dimensions. So maybe square root, or maybe taking logs would do it. But if you do square roots, this is the plot that you get. Right? And if you run that model, right, and then do the residual plot for that, some of that pattern is gone. There's still kind of a cluster, and there's kind of these couple of other ones that are down here that are sticking out. So maybe if these weren't here, the regression line, this is the residual plot, would change a little bit. But on the square, these two kind of are outside of the pattern, so maybe there's something special about those two churches. But otherwise, it looks better, looks straighter. In that textbook, there was also a information on brain weight and body weight of different mammals. So this is the top part of the data set, right? The first few lines where there's an animal and then brain weight and body weight, right? And so the interest then is there a relationship between body weight and brain weight? Biologically, maybe it would be interesting if there is, but this is the picture. It's kind of like the picture. It reminded me of the picture that from that first case study kind of reminded me of this thing, where there's such huge observations out there that it's hard to see much of any pattern, right? All these points are squished together because of the massive scale, right, out there. So these are elephants of different types and some other larger mammals, some gorillas. Humans are in there somewhere, right? So, and then a bunch of small ones. So in this case, taking the log of both seemed to produce a very nice straight line that could be used. Let's go back up to one that we didn't. We did that one with species. Yeah, there was another one in that data set. Also other species on islands. There's, but this one has students that took the 351 class are familiar with this one, that there are the number of islands in the Galapagos and the number of species they have, the number of endemic species they have, land area, and a few other variables. And if you plot this land area as a predictor of the number of species, you get something kind of like those other plots where there's an extreme point out here that seems to disturb the pattern, right? So if you wanted to fit regression to this, I guess you're going to put a line pretty much that goes to that point, right? Because if it doesn't, if it tries to go up in any way, or if it misses this point, it pays the price of a huge residual, and it just won't like this. So what do you do with data like this? Well, these things are so skewed. You're taking logs, makes that huge standout point back in. And it seems to be not quite as extreme. I think you could make a case in this that maybe this one island is so much bigger that would it be reasonable to fit the data set without this one point, right? And make a model for smaller islands, right? Away from that. So if you did that, you'd have to find that point, right? So you can plot, you do the log of NS as a function of log of area, and then we can tell it the data is going to be this Galapagos data set, but with area less than 3,000. So area less than 3,000 will cut off that point. Let's see what that plot looks like. So without that one point out there, it looks somewhat reasonable to do regression on that. So if you do take out a point, right, you would need to write something in the documentation, the report, that we fit this. Oh, this is also on the log scale. So if we don't do it on the log scale, I was also interested in that. If we don't do it on the log scale, well, it's still kind of spread out. So maybe taking out just that largest point is enough. You get into a little slippery slope. Well, should we take out this one? Should we take out this? So at some point, you can't really defend taking out points to make the pattern look nicer. But that one was so enormously out there that it's pretty easy to identify that one and say we're going to restrict the model to predicting for that one. We won't predict. We won't try to predict for the 4,000 or anything above about 1,000, where we have maybe probably not past 1,000, where we don't have much data. But again, log seems to probably be the better option because it made everything look straight, even without that. This was just the logs without that particular, even within that, with that particular point that's in there. Right. Are there any questions about things? So there's just some different examples, and we could do more plots and things on the homework, or for a project. You could look at more different types of plots. Another way to assess and quantify how well the regression does is there is an analysis of variance table and a couple things that come out of that, right, that's associated with the regression. Right? So total variability has to do with the variability of the y's. There's going to be a degrees of freedom and then a sum of squares. And the total sum of squares is the yi's minus the y bar squared. Each point minus the overall average. And we give that in minus 1 degrees of freedom because there's n points and we're estimating one thing, there's that average there. There is a residual component that can be taken out. It's based on the regression line, the distances from the regression line. So there's 2 parameters there. And that's the sum of the yi minus yi hat. Right? In a regression context, we make the distance from the point to the line rather than to the overall average. And the other part is called a sum of squares for regression. It only gets 1 degree of freedom. It's going to compare the predictions to the overall average. So this gets called sum of squares regression, sum of squares residual, right, and sum of squares total. And these things actually add up to each other. So if you take these two things and expand the squares, group terms together, there's some cancellation, and it works out nicely. The sum of squares divided by their degrees of freedom gets some measurement of variability. So mean squares, right? So the sum of squares regression divided by its degree of freedom. This one, sum of squares residual divided by its degrees of freedom. And you can do this one down here, but they don't add up, so they're usually left off. And so if we want to do a hypothesis test, is the slope equal to 0 versus an alternative that it's not equal to 0, we can compare the 2 mean squares that are up here. And that is an F statistic, mean square of regression over mean square residual. And if the regression really makes a difference, right? If the y hats really are changing a lot as you go on with x, so that it's not flat, right? Then this will change pretty dramatically. At the same time, if the points are close to the line, that one will be small because there's low residuals. And so it's kind of that relative size. How steep is it for the amount of variability that's there? Right? And that's what you get with this mean square, this F statistic. So under the null hypothesis, because our F statistic has an F distribution with 1 and n minus 2 degrees of freedom. And so we were going to reject the p-value we're going to calculate for this test is the probability that this particular F distribution is greater than or equal to our F statistic we got with our data. And if that's small, we'll reject it, meaning that we got an extremely large value of the mean square regression in comparison to what we would actually expect under the null hypothesis. So in all of these the examples with the summaries, right, so here's this log of the species. So this is our summary of that, as well as the formula, the intercepts and slope, standard errors, p-values, and some p-values with a highly significant regression. If you let me get out of that, change this to ANOVA. So the ANOVA command applied to a model object from LM gives us this ANOVA table. So there's only 7 observations in this one. So it's 1 and n minus 2. And if you add those together, it would be 6, n minus 1. The sum of squares there, the sum of squares divided by degrees of freedom is a mean square, and then the ratio of these things is this enormous f value, and you get a small p-value. Right? So again, this test in this f distribution test ends up being the same as this t-test up here for this one, right? But squared. So if you squared the t-value, you would end up getting this 425 value, and they have the same p-values. In multiple regression, when we have multiple predictors, there won't be quite that same relationship because it's just they're so if you take, for instance, a 20.62 squared, it's about that with some rounding. That's up there. The sum of the, let's see, it's log of area, right, minus the mean of log of area. That's what I'm using as my y value, and close those things off. Square them. That's the total sum of squares, right, the y's minus the averages. And log species, not log of area, log of species, sorry. The outcome of species. And so 7 is the 6.9962 plus the tiny bit for residuals. That's there. There's one other thing that we're going to run out of time for today that just, in the second case study that's in the book in this chapter, it's actually a designed experiment. And it has different voltages, and then the time that a fluid maintains its conductivity. Right? So at low voltages it lasts longer. As the voltage gets higher, it wears out faster. Right? Whereas at very high voltages, it almost doesn't last at all. Well, because you have multiple observations at each of these design points, you can do something more. Right? Instead of fitting a linear regression to this, you can take the average at every point. So you could just do this averages at other points and essentially treat it like an analysis of variance, right? Where you'd have this 1, 2, 3, 4, 5, 6, 7 groups there and get 7 means instead of fitting a regression surface. This one is kind of problematic, this picture, right? Because there's basically very little variability down here, and then the variance gets very large. So kind of non-constant variance is a very big thing for this one. And the analysis of variance, so you can do the regression, and it's a highly significant regression because it's going up, it's not going, but it's going sloping downward. But in R, to do analysis of variance, that voltage itself is numerical. So if you just put voltage in there, it treats it as a quantitative value and has 1 degree of freedom for just that slope there. But if you tell it to treat it like a factor, it'll pretend that it's different groups and do them all separately. So the linear model summary, when that happens, actually gives you a bunch of different 1, 2, 3, 4, 5, 6, 7 different coefficients, right? To give you an overall intercept, and then how the different things deviate from that. So the intercept, it's like there's an indicator there for the 28, the 30, up to 38. So the average prediction for 26, right, is going to be this 1303. But each one of these others is some smaller value down from that, right? And here at the end, it's almost 0, right? So it'd be 1303 minus the 1302. It's just barely 1 second that it's lasting at that voltage. And so there's a little bit more to the analysis of variance that comes out of that one, where it's highly significant as well, but now it has these 6 degrees of freedom. It's treating it like 7 groups and then estimating the means. And there's a comparison that can be done. Which of these models is better? Is it better to do individual means for every group, or is it better to do a linear fit to try and predict that? And so if you can do comparison of the ANOVAs. The book calls this a F test. It's an F test, but it's a comparison for lack of fit. And so there's 5. There were 7 groups, so there were 6 from ANOVA, and then that's comparing to 1 regression line. So it's the 6 versus 1, and so there's 5, a difference of 5 parameters that are there. And it's significantly different from 0, which suggests that the one that just uses a regression line is not adequate, right? That there's a change, right? So the null hypothesis would be, no, you don't need 7 separate means. You can do it with 1 regression line. That's simpler. And because because we had a very small p-value, we reject that smaller option in favor of the bigger model. Right. And if we one thing that might show up, just to conclude one thing here, if I save the model of the time as just as a quantitative predictor, right? And then plot the fitted values from that model versus the residuals. If I do the residual plot for that one, you will find pretty funny residual pattern, right? It's kind of sloping down, and then it goes really big. And it's doing that because when it tries to fit this, so maybe line is mod, get red so it stands out, right? Oops, I run it. That's the fitted line, right? It's not really great in terms of doing this, right? But it has to be pulled up to meet those. It kind of meets the ones in the middle, and so you're going to see the odd fit to the data by looking at the scatter plot, and it's going to show up even more in the residuals. Right? So I know I've gone kind of fast through a few things today. There's also a handout that talks a little bit about the project, and maybe we'll say more about that on Wednesday. It's not due for a few weeks, but the things that we've already done in terms of methods to be used, or looking ahead to multiple regression, something in that area could be done as well. Okay, so.
I just like kept flashing, flashing back. Thank you.
That particular, yeah.
So history.
So you'll have to tell it one of the. Right, so the variable is either going to be height or force.
Yeah.
And because it's there for several different data sets, I would do a histogram of like Hemi $, force. Right, I think you need HIS T.
Oh.
Go ahead and just type that in for this file here. Did that go?
Yeah. So if I want to graph the force with the transformation, so I just need to add.
Well, you put log around the entire thing, so hist, and then log, yeah, and then a log, and then the Hemi $sign forest.
only.
Yep. So those are the predictions, right? So each y point is mapped down to the line,
Yeah.
right? So these two go there, and these go up here. So that just illustrates where the prediction points are.
Oh.
That would be kind of optional. You wouldn't necessarily have to put those X's on there. The regression line really says where the predictions are.